on record. Okay.
hmm
Hello, my name is Andres Luciano. It's my partner, Fat Tran,
Hello.
and today we will be talking about similarity measures of strings using novel methods, and then also doing similarity joints, which we will talk about later. So let's get started. This is the paper that we implemented. As we can see here, we start talking about strings as they are similar syntactically. I think that's the main way in which most people talk about string similarity. So, for example, Sam and Samuel, they're similar because their syntax is similar. But for example, words like Bill and William, which are not so similar. And that's why introducing things like synonyms and synonym pairs can become useful for when talking about string similarity. Also, for example, here we have New York, which abbreviates to NY, and a lot of cities and names that have abbreviations should also be considered for uh, string similarities, since they basically mean the same thing. They're just spelled out differently, or they're spelled out in general. So the first method that we are going to talk about for this is called full expansion. So full expansion basically talks about comparing two strings, S1 and S2, and when we have also a rule set. And rule sets, for the purpose of this paper, are defined by a left-hand side and a right-hand side, where these rules, um, for example, the left-hand side of the rule will abbreviate to the right-hand side. And that's basically how we define and treat them as. So full expansion, we take the token set of each string, and then we find the applicable rules to those strings from our rule set. So we define an applicable rule by a rule in which the left-hand side is a substring of the string that we're comparing. So we find those applicable rules, and then we expand our token sets by those right-hand sides of the rules, and then we perform the card similarity on those expanded sets, and that is our string similarity. But there is one issue with this method, and we will explain that now. So take, for example, International World Health Conference 2012, and then sort of a kind of expanded version of it, which includes UK. And we know that UK expands to United Kingdom. But in this case, this rule is not necessarily useful because UK or United Kingdom is not in the first string, but it is in the second. So if we were to expand UK to United Kingdom in this case, it wouldn't be a useful rule because it's only in one of the strings. So that's why we then implement um, a more optimized version called of the full expansion algorithm called selective expansion. So selective expansion takes a more detailed approach when picking out rules. It uses an algorithm called the rule gain algorithm, which finds the rules which include new token sets, but also include useful token sets. And so that's what the rule gain algorithm measures, and then it implements it into the SE algorithm, which stands for selective expansion. So we find a candidate rule set of the rules which have a good positive rule gain. And then from those rules, we expand upon them. We expand upon our token sets for same as full expansion, string S1 and S2. And then, or yeah, we find those candidate rule sets and then we expand upon them using these two methods. So both of these um, algorithms were implemented in Python 3, as we can see in, So yeah, so this is full expansion. We find the tokens which are in the right hand side, and then we expand upon them, and then we measure the Jacquard similarity between those two. And then and here is Jacquard, which we know to just be.
You didn't share the Python code on the screen.
Oh, okay. I'm so sorry. Okay, I'll just share my full screen. So sorry about that. So here is our, didn't open it. So here's our full expansion. We find applicable rules on the right hand side. We expand upon them on our sets, and then we compare them using Jacquard similarity, which is written right here. And then we also have our selective expansion here, right here. So here we have our expands algorithm, and then we have our find candidate rule set algorithm, and our rule gain algorithm, and then we combine those into the SE similarity measure, which returns the similarity measure that we mentioned previously. And that's about it for this algorithm for now.
Okay, so the part that I did for this project is I work on experimenting the SN join algorithm and the SI join algorithm that the author proposed. And to understand join algorithm, we can basically understand as we're having two sets of string, and we want to find what pair of string in between them are similar. And we use a threshold called theta to define if the similarity measure between the two string is greater than theta, then we would say that the pair of string is greater, is the synonym string. So to fully understand the SI join algorithm, we first need to understand SN algorithm. So SN algorithm is a filtering and verification framework similarity join, and it is one of the called like the majority of the state of the art approach right now. It's doing filtering and verification. So what SN different from the others is it extends the way that it generates signature uh, from the prefix filtering. So prefix filtering is a filtering scheme where it takes each of the string and turn it into a set of token. Then the token of each string are sorted based on a global ordering, and then a prefix set for each string is selected based on a given similarity threshold to the signature. So I will share my screen and explain on the SN join. So for SN join, so what we do to generate the signature is first we will do the math of prefix filtering scheme, and after that this is the math of the prefix filtering scheme, and after that we will for each of the rule sets we will generate an expand set of SI, and we will calculate the signature of that SI. And at the end, we will union all the signature of that SI, and we will get the signature of the SN set that we have. So after we do the filtering for two set S and set T of all the string, then we will go to the we will find the overlapping of all the strings pair. And when we get the overlapping of all the strings pair, we will go to the next step, which is the verification step, which we will check if the similarity of each of the small s and small t compared to rule R is greater than theta for the join. And that's for the SN join. And for the SI join is like an upgrade version of SN join. So the first thing is better than the SN join is gonna avoid signature overlapping checking by create a thing called the I list or the inverted list. So this is this is illustration of how the iList work. So basically, each of our string will have a set of signature, and we will take each of the signature, turn it up into a token, and we will have a list of token. From all this list of token, we can generate a list according to each of the token, the list of the string that have that token as signature. And the second thing that SI do better is reducing the number of the candidates. So the way SI join reducing number of candidates is using the S directory, which is a tree data structure to prove on the case where S1 and S2 definitely cannot be synonyms. And the way they do that is in this tree structure, we will have only three layers. The first layer is the root entry, which point to the on of the next layer. The second layer we call the fence entry, and each of these fence entry will have three values. It will have a U value, a V value, and a P list to point to the child. The U value is the length of the string, the max length of the string, and the V is the max expand length of the string that have the length U. And underneath it, we will have the leaf entry. So this leaf entry will have a T and a P list. This P list will point to the I list according to this string. So this T right here is the number of the expanse length of this specifically string under this use length. Uh, so we can see an illustration down here better. So let's say this is my set S, which I have for string Q1 to Q4, and we can generate the signature out of each of the string, and then we will see the length right here. So this length right here is length of the token in the string, and this F right here is the length of this adding the expand signature from the synonym. So this is the expand length. So for our I list, we can see that we can see like ACM in Q1, then and there's no ACM in the signature anywhere else. So it's only point to a list of only string Q1. And if we see the conference, we appear in three of the other string. So we point to Q1, Q3, 2, and Q3. And this is the root directory. So the root directory basically first go to the fence entry, which is point to the length in order like 2, 5, and 9, and then it will point to the maximum expanded length that it has. So we have 7, 7, 11. The reason 2, 2 here is not here because the 2 here is less than 7. So now under the same length 2, we will have the 2 expanded set. So we will have the Q3, which is the Q4, which is the 2, 2, and then the Q3, which is the 2, 7, and this one is according to the first two strings. Now we will generate from these two, we combine, we can generate a thing called an SI index. So basically it's just an S directory, but instead of pointing to the string, we will point it to the signature token inside the I list from this. So we can see that for Q4, if you look at here, Q4 only have this token as signature, so we point to it. And for example, if Q1, we have 4 token inside here, so we will point to 4 of those token in here. And so the way that SI join algorithm is like better at reducing the number of candidates is by pruning the unnecessary one, unnecessary branch in here when they look for synonym pair of string. So the idea is when we have a string S1 and a string S2, if the full expansion set of S1 is less than the size of S2, that means S1 and S2 cannot be a synonym because after expansion, S1 will somewhat have some value of S2 synonym in there if they could possibly be synonyms. So that's why we will use this tree to prune it out. So for the SI join algorithm, we will have 3 steps in doing that. So basically, the first step is we going through the 2 tree. So we're going to the tree of S, and we're going to the tree of SIT. And we will compare the max expand length, the max expand length of the entry level, and the production of theta, and the max of the original length of the entry level. And if this go through, mean that we this inside here we generate the candidate pair. Whatever doesn't go through this if, we can just prune it out. And we do the same for the next leaf level. And after that, after we get everything, we will find the overlapping. Now we just find the overlapping between the string, and then we will add this tuple of candidate pair for verification later into our overlapping set. And this one right here is only the filtering part. We will have a verification part later to check out how that works. So I will share my code for this part. And for this part, if we go to SN join algorithm right here, you can see here I wrote a prefix signature generation. So in here, this is the mass of prefix signature generation of a string. So for SN signature generation, we just do this, but we use full expand before we do the prefix signature generation. And then we will apply this signature generation into SN join, where we will generate on the signature, and then we will find the overlap between the two set S and T. And after we have the overlap set, we will do verification and get the result string, which are synonym to each other. And after we get the SN join, now we go to the SI join, which is a little bit more complicated. So here I define all the class for the fence entry and the leaf entry. And here I define the ilist to generate ilist. So here I directly go and do the SI indexes, because doing the S directory alone doesn't apply into SI join. So in SI indexes, what I do is I take the list of string S, and I will build a tree upon that according to the data structure that present in the paper. And after I build that, I will use that SI index, or I also call it SI tree, inside the SI join. And I will apply the SI join algorithm to it. And after this algorithm for filtering, I will do verification using whatever similarity measurement that we have. So for our test, we have 3 kind of similarity measurement. We have the we have the Jacker similarity measurement. We have the full expansion similarity measurement, and we have the uh, selective expansion similarity measurement. So so in the first part is we doing for in the first part we're doing similarity measurement. So Andres, you want to take over this part for the experience?
Yeah. Okay. I can share my screen now. So yeah, basically for this part, we basically just take three sets of 2 strings and a few rules, and then we simply run our SE algorithm, our full expansion algorithm, and our Descartes similarity, and we can see what different values we get from different from the different measures. So if we run evaluate similarity measure, yeah, so we can see the strings that we're comparing, our rule set, and then finally our similarity measures. So here we get we can see that Descartes is very, very low. since it doesn't take into account synonyms, but both full expansion and selective expansion have pretty significantly higher values because they take into account synonyms. And then finally, we can also see that there's some cases in which selective expansion will be slightly better because it is more considerate when taking or when considering what rules it's going to use to expand. Yeah, just one more thing I wanted to bring up, which we, or at least I didn't fully implement, was the estimation signature selection. I'm not gonna go into too much detail, but basically, given an I-list or given a few I-lists from the algorithm that Fat was talking about, we are able to basically calculate the the cardinality of each of the signatures, and we can get like an upper bound and a lower bound for those cardinalities, and then we also calculate tighter upper bounds and lower bounds using the Flageolet Martin algorithm, and then expanding it to use 2D hash sketches. I go into more detail on the paper, and so yeah, basically I just create the 2D hash sketches, and then I just get their witness probabilities, and then we can use those values to calculate the upper bounds and lower bounds, and then we can talk about the SI join stuff.
Okay. So my part for the experiment is I do a little part in the similarity measure evaluation, and mostly will be on the joint evaluation. So as for as for similarity measurement, what I did is I will calculate the precision, recall, and the F measure of each of the similarity measurement that we perform. So the way to calculate precision is we have the true positive over the sum of true positive and false positive. The recall is true positive over the sum of true positive and false negative. And the F measure is the 2 times the precision times the recall over the sum of precision and recall. And to calculate the quality of measure, so if the so basically what true positive, false negative, false positive mean in our case is we will see if the similarity measure of the two string in each of the set is greater than zeta. That means our similarity measurement algorithm predict that these two strings are basically the same, basically synonyms. And we also generate a validation set, which we go through our data set to validate which actually two strings are the same. And we will use that to see to get the number of true positive, false negative, true negative. And after that, we will use it to calculate the three number of precision, recall, and F measure. So down here is we using that to calculate for Jaka similarity, for expansion similarity, and selective expansion similarity, and which each different theta rule set with different theta amount. And for evaluate join, so evaluate join, we also use the same data set that we have from before. And what we do is we will generate the join, and we will check out the time when we generate each of the join depends on how many synonyms we give it to them. So we increment it from 10 synonyms to 20 to 30 up to 90, and our synonym text we have here is 96. So 90 is almost full of this. And this is for the this is for the SN join, and we do the same thing afterward for SI join. And we use it with all three different similar measurement including Jakarta, full expansion, and selective expansion. These codes take a while to run to generate a graph. So I can just run it and give you a simple idea of what it will be generate. So right here, we can see this list right here is like, for example, this pair right here is a pair of synonym that our algorithm finds. Uh, and each of these lists is one of the algorithm that get running. And after all of that, we will craft them and we will plot them out. So from the picture right here, we can see with the increased amount of synonym down here, we can see that for SN, for FE with full expansion, and for SN in Jakarta, it's pretty low. But for SN with SE, it have a little curve going up. However, for SI, the three of them take equally long amount of time to do. The reason our experience doesn't have the same result as in the paper because our database is pretty limited compared to their databases, and we are unable to acquire their full data set. And also, we don't have the computation power as their computer that they use inside their research. So to run our evaluations take quite a bit of time. So I didn't run full this for the max synonym that we can generate. And our result may be a little bit different from there. So that's a wrap up for our part of joint algorithm, our experience, and our similarity measurement. Do you have anything to add, Andres?
Yeah, we were just able to implement um, higher quality similarity measures and joins, and we were able to test them out with data that was similar to the one in the paper. And I believe that our implementation was faithful to the reference that we had on the paper, given the time and the resources that we had. And we saw improvements in the improvements and advantages of our algorithms for string similarity. And yeah, that's pretty
Thank
much
you.
it. Yeah, thank you. I will stop recording.